Okay. So now I will switch between two tabs in my browser. One is a presentation for the hands-on session for PIConGPU users. For that, if you want to follow along and don't want to type in what you see on the screen, you can go to the Alpaca workshop GitHub repository. Let's see whether I've opened it. No, I don't. And go to presentations there, and there you can download the one 2024-10-25 PIConGPU or pic-user-plasmapepc.pdf. That might be easier to follow along because I will switch between the PDF presentation you're seeing right now, and I think I'll work with the Lumi web interface. So there might be some switches between what you say, and if you want to follow that, please download it beforehand. You can also go to the Alpaca workshop GitHub and go to day 3 and there to the exercise number 20. There's just a README and a IPython notebook in there. The README is a very brief summary of the commands we will execute. I'll give you a minute to actually look at that. Perhaps I can even show it to you.
You typed in GitHub with H instead of D, but it went to the correct page.
Luckily, or now my credentials are stolen. So there was a comment from the audience that I mistyped the URL and still ended up hopefully on the right web page. So what we're looking at right now is the user session. So this is, let's see whether it actually shows. Yep. So this is the one you can follow along. Alternatively, not very helpful alone is day 3, directory 20, and there is LWFA analysis, IPython notebook, and a README. And here you see a very brief summary of what we're actually doing. And I think there's some mistyping. I already see that. So follow the PDF, please. Okay, that's for now. Go to full bit. Okay. So this is the hands-on. Do you hear me? Yes. This is hands-on training for PIConGPU users. What we will do today is, I think nobody today has just joined today. So the first thing I wanted to do is to check your access to Lumi. I think everybody here has now Lumi access after these 3 days. If you don't and have just joined, download the PDF, follow the instructions. I'll skip that for now. Then we will set up and run our first PIConGPU simulation. Then we'll do a quick data analysis of that simulation using OpenPMD and Jupyter, using Python. Then we'll do a deeper dive into how to set up PIConGPU simulations on a few example parameter files. Then we'll have a session for some questions, and then I'll suggest some project you work on your own. And we will be here available for us answering your questions if you run into any problems. So we'll skip that part. You should have access to our training. You should have shared your SSH keys. You should have seen that thing if you run over terminal. You see our project allocation. This is the important part that I will work on now. This is your Lumi web interface. So please use the login node shell there or SSH into your head node if you want to follow along. I'll assume you have in Scratch at least a directory with your username. If not, PIConGPU or TBG, that's a code we want to use partially today, will create it for you. Just for a recap, for this project, for this workshop, these are the directory where your project stuff and your larger data sets like PIConGPU simulations should reside. So let's start with PIConGPU simulations. First of all, everything I'm telling you right now is geared for Lumi, but we have a so-called PIConGPU in 5 minutes on Hemera, which is our local cluster, and I'm following closely along that description, this tutorial. I would recommend you to actually follow that link here and look at that, perhaps have it open nearby while you're working on it. This explains a lot of the stuff we're covering right now briefly. If you're in the PDF, this should be a linked URL, just can click on it. Right now in my browser, I'm not able to click on that link. So this is briefly how you perform PIConGPU simulations as a general workflow. And the word workflow is here used intentionally because this is then done also by workflow engines automatically. So first of all, you need to get your PIConGPU source code. For that, we just clone our PIConGPU repository. If you have done this by chance before today morning, please redo that or update your source code now. Due to Lumi having a quite recent CMake version, there has been some issues that have been merged to our current development branch this morning. So if you already have PIConGPU, please update now. Then we'll prepare and load our environment, and there, thankfully, Franz installed already OpenPMD and stuff like that, so we'll rely on his libraries, but I'll show you how to set this up manually with your current profile system, but we'll link to Franz's libraries. Therefore, you don't have to install all the dependencies manually. We'll just show you how to do this in general. Then, the common workflow, that's point number 3, is to create a simulation setup using a code we created that's PICcreate. That's a helper code that says, okay, yeah, this example in PIConGPU looks closely to what I want to do, so I'll start from there. That should make your life easier. You're not always starting with an empty simulation where you have to define everything else. Steal our examples and adjust them to your liking. Then we'll do some setup parameter adjustments. That's the main part you should do. Then we'll compile it and submit it to the cluster. And then we'll do some data analysis. In this case, it's going to be interactive using the Jupyter Lab right here. And this is an old presentation, so I'll skip out of that. Give me a second. Oh, I can actually do it differently. Oh, come on. So give me a second. As mentioned, there have been some fixes this morning. And this is still the old version for that. So I'll close that. And probably will do the same thing as you will do now. I'll close that, then we go to... Did I type it now correctly? Hopefully I uploaded the right ones. So, the PIConGPU user session. It's always in the way. This is now the correct one. Yes, okay, this is now the correct one. So I won't go into full screen mode because it takes forever to actually go through. Okay. Sorry. Okay. So the first thing we're going to do is we're going to download the PIConGPU source code. So for that, please go into your home directory, command number 1, create a directory src for source code, go into that directory, and then clone our PIConGPU repository. I'll try to follow along using our web interface. So we'll get a login node shell. Please don't use a compute node for now. We're going to do the compilation on a compute node because that's just an expensive task. So I'm already in my home directory. I probably do. I hope this is now better readable. Yeah. So based on that, I'm already in home, but I'll follow along. So we do change directory into home. It might be that I still have a src directory. Yes, I already do. If you don't, just create one. In the end, you're free to do that directory selection as you like. I'm just following along the tutorial we have on our read the docs. I personally structure my workflow differently, but this is just so that you can follow along with our other tutorials. So the next thing is we're going to clone our GitHub repository. I assume you already did this a couple times. If you did not do that before, you will find this. If you go to Computational Radiation Physics, PIConGPU, you can clone that URL directly here. Since if you didn't upload your SSH keys to GitHub, please use the HTTPS version of it. Otherwise, you have to upload your keys before. So that's how you get this URL I just pasted in right here. So let's clone GitHub, not GitHub, PIConGPU. So we're done. So now we've got a directory, PIConGPU. Great, first task finished. So let's continue. The next thing is, PIConGPU requires a few libraries, like as you have seen in the introduction, Boost, OpenPMD, if you want to have any output. There's also an option to have look at PNG images. And all of this is either provided on the cluster itself by a module system, or you install it manually yourself. And what we'll do right now is we'll copy. So for most clusters we run on as a group, we provide an example profile, which gives you the structure of how you could set up the module system and your dependencies on each of these clusters, and then you can just source that profile. This is updated regularly, and you're lucky for the Lumi setup that is pretty much finished except for the dependencies you have to add manually for that workshop, like OpenPMD. For other clusters, this is commonly fully set up already. There's a question from the audience.
More like a remark specifically. So there is also one specific example set up of how to get something working by PIConGPU for stacked systems in our example files in PIConGPU. It's called bash dev server ACDR, I think, or something similar. So if you have a stack environment, you can also use that.
So if I assume you didn't hear the comment from Brian from the audience. So right now I'm speaking about using it on clusters with a module system available where most of the software you need is available. However, you can also use as an installer Spec, and there's an example for that also in the example setups we'll just cover. So the first thing we want to do is to copy from our PIConGPU source code. There is etc PIConGPU, the Lumi Euro HPC system. There's this Lumi -G for graphic cards, HIP CC PIConGPU profile example, and we'll just copy this into our home directory. Bless you. Okay, let's do that. So copy from PIConGPU, etc PIConGPU, Lumi, and inside Lumi we find this Lumi G, and for that I'll just go put this. What did I do? Oh. Okay. Sorry. Copy PIConGPU, etc PIConGPU, Lumi and Lumi G, and we'll put this into $home. Okay, and since most of you use the VS Code version, I mean, you can use any editor you want, but for now, let's use the VS Code. How do I do that? Open. So we'll open that file in VS Code. Give me a second. And now you should see the that profile. I copied it there. Actually, I said profile in my script, so you should have that. If you typed it correctly as on the PDF, you should have that profile. I just copied the example right now, so I had accidentally that example. I'll keep that for now. So let's go through that example. You should have a different name. The naming is again not important. And if we go through the slides, we'll see a few things we want to edit. So we want to change that we get mail notification. You want to add your mail address actually to contain your actual mail that you receive these notifications. We have to add our project ID so that the accounting is correct for the Slurm system. We can also extract something that contains where our project directory and our Scratch directory. So this is only convenience. It's something you don't have to do. The project ID is, however, something that is required for accounting. You can also specify a preferred editor, also optionally. And then we have to add where do we found the PIC libraries that we are using. And again, this has been installed by Franz before. So this is in our project directory, workshop software, and they're in local. They are also together. And then we have to specify where our PIConGPU source code is so that our profile or the environment we load actually knows where to get that source code from. So let's do that. So here, for example, line 8, we will say, write me everything from run successfully to crash and so on. Then type your email in there. Then the next line just combines this as a name. So we need a project ID, and for that, I'll just copy it from here. Hopefully this works. So let's paste this in. And then we uncomment line 17 and 18 to define where our project directory and our Scratch is located. And as you can see, for Lumi, they use just the project identifier as a directory. So there we reuse already the first variable defined in line 16. Then you see a lot of stuff right here, like loading your programming environment, your compilers, and so on, your MPI. Boost is installed on this system, so that's something you don't have to install. You define your compilers right here. So this is all prepared for you so that you don't have to do this manually. If you're on a new cluster, you have to find these dependencies on your own or install them. So now I think I missed that one. Ah, yeah. So line 72 was the next one I wanted to change. As you can see, there we define a variable called PIClibs for our libraries. And this line already contains, again, prepared for you, the project ID and the workshop software and local. So there you don't have to change anything. And then we just paste this in our LD library path. Again, with libs64 and lib. And this makes available, for example, OpenPMD. I think also the PNG viewer, yeah, writer, PNG writer, yeah. And then down here you define where your PIC source is located. Again, we followed along the tutorial, so this is pretty much, if you followed along, that's where your PIC source code, or PIConGPU source code, should be located. If not, please adjust that line. And that's all you need to do. And then there's some extra functions defined down here that we will use later on. Yes?
You also have a big system template path, which is also relative to your PIConGPU source directory.
Yep.
Sorry, just to mention. Because if somebody placed this PIConGPU source somewhere else, that would also have, yeah.
Okay, that is big. Okay, so hopefully you now changed everything. And let's look at these slides again. What's the next thing we do? We have to source that profile. So let's do that. Where is my terminal? There's my terminal. So I'll go one up. Source LumiG profile. You will see some warnings and some reloading of modules. And if you're now lucky, everything should work out. So now you set up your environment to run PIConGPU. What's the next step? If you remember the initial introduction, the next step is to actually copy an example and work from there. So let's go back to our home directory as the next step. Create a directory there called PICinputs. Use this for our future examples, and let's start with a laser wakefield example. So now, since you sourced our profile, your path environment has been extended to also include helper methods or executables from PIConGPU. And one of these helper functions or methods is pic-create. Pic-create is a simple tool that copies an example and to whatever directory you want. So we have a standard laser wakefield example. That's what we reference right here. And we'll give it a name LWFA, which is the abbreviation for laser wakefield acceleration. And that copies everything you need. It will copy your, as Brian mentioned in his remark, your template files for that specific cluster you're currently working on. It will copy your configuration files. It will copy your param files in a consistent way, but not just, but a bit smarter way. So in principle, you can do also copy, but let's use that one for now. Okay, so let's go. So we first of all, we want to PICinputs, I think, with plural. Okay, and then we use pic-create, laser wakefield, and we call it LWFA. As you can see, there's an auto-completion with this tool, so you don't have to traverse the entire path to wherever we place that example in PIConGPU. Okay, and now you see This has been empty before. There is an LWFA setup. Just to briefly look at that, there are CMake flags, for example, compiled cases. We ignore that for now. There's etc. There's our runtime configuration and cluster setups copied in there. There's includes, which are our compile time parameters. And there are some libraries for whatever analysis we want to do, perhaps. Okay, so let's go back to our PDF. We can have a look at the param files next, and that's exactly what we're going to do. But I mean, I show you here how to do this on the command line. I'm going to be using our web interface with VS Code again. So if you're doing this via SSH on your command line, please go to include PIConGPU params, have a look around, and then we're going to edit the incident field.param file. For now, for this first run, I won't go into details. This is just to follow the workflow we'll currently do. This is now changing one compile time parameter. And if you're already opening that incident field.param, please go to line 66. There's a number, a floating point number defined for a so-called a not value. This is a normalized laser field strength. And this is set to 8.0, and please change this to 5.0. That doesn't really change so much about the physics with these still vague fields. But, so I have to go to pick, where is it? Pick inputs, LWFA, include, and then I'll have to go to incident field. So this is C++, I'm not going to have code highlighting for now. And this is line 66, so please change this pre-compiler definition to 5. If you don't, this really doesn't change much for now. Save that file, and we're done with that. In principle, if you want to set up your file, you have to read through all these param files and adjust it accordingly. For now, we're just playing around with that. Okay, after we've done that, we will want to change some runtime parameters. And this is now essential, because otherwise your setup becomes a bit more complex because we need to use net memory on Lumi, as Franz helpfully pointed out a few days ago. Otherwise, your simulation will crash. So, again, if you're on the terminal, please go here to pick inputs LWFA and traverse to etc PIConGPU. Look around, and we're going to use the 4CFG example. I'm going to use, so there's TPG OpenPMD defined, that's line 68. And please just remove everything we need for checkpointing. This is a really short and small simulation. We don't need checkpointing. Remove checkpointing and add openpmd.data preparation strategy mapped memory. So I'm going to do the same thing. First of all, I'll traverse there. So we go to etc 4.cfg. Oh, it's so. Okay, and you can see, okay, this is defining stuff that we need on runtime, like how many cells are we going to compute. And this is a small example, but you already see we're away from 2 by 2. We are now at 192, 2192. Somewhere down here you find OpenPMD. We're going to remove all this checkpointing stuff. And then we're going to add the mapped memory option. And if you, for example, want to do phase space analysis, there's a plugin for that, runtime in situ plugin I didn't cover. You can adjust the parameters you want to analyze. Energy histograms, same thing here. PNG output, all the stuff you define at runtime. How long do you want to run, and so on. How large should your volume be, can be defined right here. Don't forget to save. And I think then we are done with our preparation. So the next thing we're going to do is we're going to compile it. In principle, on Lumi, it's possible to compile PIConGPU on the head node, but please don't. That's not a problem if you're doing that alone for now. However, if all members that attend this session right now will do this on the few head nodes that are available, that's going to use a lot of RAM and a lot of cores, and we're going to have some performance issues. So please, and that's why it's important you're on the head node right now, we want to execute this, another helper function that's called getDevice. And getDevice pretty much gives you an interactive session for a brief period of time for that specific cluster, and then compile using getDevice. So again, let's go to our LWFA example. So traverse out of etc Lumi, or just go to your, so I'm already there because, so the next step is getDevice. This is gonna require a few seconds, hopefully, and then you have a node. So as you can see, I'm now on one of the compute nodes. We adjusted our parameters, we adjusted our CFJ. So the next step is pick build. And you have done this for Alpaca, so you did this CMake, then CCMake adjustment. We tried to do this easy, made this easier for the PIConGPU users, so let's type pick -build and execute that. And now I'm ignoring a comment from Klaus. Oh, there's one essential part. If you did everything right hopefully now, you will see that it will find PNG and OpenPMDL. Yep, there it was. Can I scroll up? Yeah. You will see optional dependencies, OpenPMD on, PNG writer on. If this is also showing up in your compile process, or in your CMake process in that case, you've done everything right. If not, please raise a hand, write in your Slack channel, or unmute yourself. So while we're waiting, I just executed pick build for now. A better option is you do a force option on the one hand, so that it avoids any cached param files. We're doing this for the first time right now, so this is not essential, but with -f, you might add param files that haven't been there before. At that point, it falls back to your PIConGPU source default example. But if you now added them and changed them, and you run pick build again, it won't know that there is a new file should take care of. So with -f, you're actually always considering all new param files. That's one option. And the second option, as you might have also seen with the Alpaca part, with this templated programming and with Alpaca, error messages become quite long. So if something goes wrong, it's sometimes useful to pipe your error message to an error text file, for example, and then look at anything that went wrong. Hopefully this is not the case for this setup. And up until recently, this compilation took quite some time, but René invested a lot of time and effort to make this faster and use more resources now. That's why we go into the getDevices now. So take your time, get a coffee. We'll wait until the compilation is done. Hopefully this is pretty fast on Lumi. And don't be fooled by the percentage sign. That's going to take a while now.
The question is how many nodes getDevice and how many cores getDevice allocated? 4. Okay, yeah, takes a while.
But we cannot do this in the time. So the question from René was how many cores we actually allocate with getDevice, because that's taking the minimum amount of resources we get with one GPU. That's not a lot. So if you do this on the head node, I think it takes every core of the head node.
Yeah.
Mm-hmm.
That's pretty fast, but please, again, don't do that.
You can limit it with pick build -j and then add the number.
Yeah, and similar to the make -j option, you can also do pick -build space -j and provide the number of cores you want to use. That would be an option for compiling all together on the head node for this workshop, but please use getDevice. So, compiling is done. I'll wait a few minutes for the rest to... Okay, there's a discussion going on. I'll wait a few minutes so that everybody can catch up.
How long will it take an ordinary laptop to compile?
So the question was, how long does it take an ordinary laptop to compile? I don't know. I never built on my laptop due to the operating system and due to not having a GPU.
If you have enough cores, it's typically faster than on an HPC system.
Yeah.
So the device compilers really take a lot of time, and if you're not building for a device that's just for the CPU,
But as established, you should not use without -J to 8 or something like that. Because then you require something like 100 gigabytes for compiling.
And also you have another
Okay.
Maybe on CPU less, but for CPU
it's
you're
less, and we've got these 64 gigabytes of RAM. So
In the audience, the discussion is going on right now. How to best compile PIConGPU on your laptop. As a physicist, don't. You always want to run on really large systems. No need for a laptop.
Well, workstation also works fine.
Okay, let's continue. So we've got a compiled binary of PIConGPU, and the problem is with the default setup we usually don't have a reservation, so that's not taken care of in our template file. And now we're going to go a bit into the details of how we're going to submit this. You already touched the CFG file to define how you do the runtime parameters, like in this case, how to call OpenPMD. But there's also a parallel file called the template file that describes how on a specific cluster your Slurm submit file in this end should look like. And we're going to touch that file for now to add how to add a reservation for this workshop run right here. Usually you don't have to touch this TPL file, but for now let's do that. Again, you can go to etc PIConGPU Lumi Euro HPC and then to standard-g.tpl if you're on the terminal, and then replace line 25, which is currently sbatch -- partition equals the TBGQ, with these two lines, reservation ENCCS_day3, and then please use that node exclusively. There's a question in the audience?
Yeah, just a little bit. Maybe you're doing this specifically to show people the TPL file, but also if you want to use reservations there without touching files or without touching any kind of setup, because reservations are on off. So there's also an option to set this reservation variable.
Yeah. So Franz pointed out correctly that this is not needed to do. You can do a environment variable to define the reservation, and then you use it automatically. Of course, we're going to have a look at the TPL file for now, just to have a look at the TPL file so that you see how this all works. As mentioned, you usually don't touch that. So let's go to that TPL file. You actually will never touch. It's here in etc PIConG Lumi HPC. There it's standard GTPL. And if you ever written your own Slurm submit file, this looks pretty, except of the license thing, this looks pretty closely to how you would write that, except that there are these strange variables that you already have seen partially in the CFG file. So that's the same syntax. So you've got your sbatch command -- account, then you have your TPG name project, and so on. So this looks pretty much like a template for a Slurm script, and that's what it is. So what TPG, what we'll use in the next slide, will do is take your template file, your TPL file, and your CFG file, and combine them together to a Slurm submit file, and then submit that for your simulation. That has the advantage that you, as a user, only touch the CFG file, and that's independent of your cluster. So you don't have to think, how do I distribute my 512 cells onto the GPUs? And had there been 4 GPUs or 8 GPUs per node? And how much memory was there? Ignore that. Just type in the numbers you want. Hope for the best. And it will distribute this based on the template file. It should make your life as a user much easier. But, just to play around, which file? Partition. We remove partition because that's duplicated. We don't need partitions for that. And then we add our 2 lines right here. I need the hashtag. Okay. And we should be done. Don't forget to save. Now we have our reservation defined and we take that node exclusively. So the next step is to run TPG, and please, we got a get device on our terminal. So we are still, here's my terminal, we are still on, you see it, on a compute node. Please log out. Control D should do the work. So you should be back on a login node. There's some interference with the setup, partially due to modules, partially due to system environments, that prevents you from submitting jobs from a compute node. That's not true for all clusters. Mostly it works. In this case, there are some conflicts. So please be sure that you are on a login node.
How can I understand that you're login?
The name is different. So the compute nodes have these names. And the login nodes, you should probably be on another number, but you should be on something that looks similar to that. So, red warning, check. Everybody logged out? Good. So the next thing is we're gonna run TPJ. TPG is our template batch generator. So we're taking the CFG, we're taking the TPL file, and we're creating a submit file, which we simply call submit.start if you're interested. And it has a few options. There's the -s options for the submit command, which is sbatch for Slurm system. But this is provided in our profiles. You don't have to know that. -t options. There is the standard -g.tpl. Our profile already knows that. So we don't have to specify. So we just say -s taking default, -t taking default. However, our specific configuration, how many nodes, how many times, that's something we should give. There's no default for that. So -c should give etc PIConGPU 4.cfj, and then please write your data to the scratch file system. Okay. And if you're then running your job, sq-u, your username should give you the status of all your jobs. So you will see, for example, also your VS Code stuff and your Jupyter. And you can even get details on specific jobs if you're using the job ID. Okay, so let's do that. TPG -s, -t, -c, etc, PIConGPU 4.cfg, and then we want to put this to, I'm not using the variable, project 5.10, and then 01 LWFA, thank you. Hopefully this works now. So it's now copying into that directory, creating that submit file, and then automatically submitting this to the Slurm scheduler. So now you see, okay, submit batch job some number. And if you check, you should see, oh, it's already running for 13 seconds. Hopefully a bit longer than that. Yes, okay, this looks good. And the other two things, this is Jupyter and VS Code. Okay, at some point, if you're on the web interface, you can actually click on Home Directory. Then you see all the relevant directories you should have access to. So we're going to go to Scratch and to the specific project. And I see a lot of people, not so many people created directories. You can go in there, you see I did some more simulations. And this is how the structure looks like. You've got an input that's pretty much your param files. So this is just a copy of everything you did. as a reference. If you're later on looking at your simulation and you don't know, oh, what was the A0 value I changed? I remember I changed it, but what was it? There's a copy of that in there. TPG is pretty much what your template sketch generated. This is your error stream, this is your output stream. We'll have a look at it in a second. And zoom output contains your simulation output directory. And we already recognize this thing we created for the heat equation together with Franz. There's an OpenPMD directory, and that OpenPMD directory contains ADIOS files. Okay. So the next step we're going to do, so now simulation is running, is we're going to briefly look at that. For that, please go to your web interface again and select Jupyter. Most of you should probably still have one running. So again, take the reservation of today, select your project. We don't need a lot of resources for that case, hopefully. Then go to advanced settings. Your home directory is fine as a working directory. Define your custom input as file and then go to the script path. And depending on how this works, for me it worked without source, for some people it worked with source. Please choose the option that worked before. Ooh, I still have one running. So I connect to that one to quickly show you what I'm doing. Okay. So again, you see what we found right here. So there is a notebook provided for you. It's either in your Alpaca workshop directory in day 320, or you just copy it from the project directory, workshop software, notebooks, and there's just one notebook in there, LWFA-analysis.ipython notebook. And please copy it to your home directory so that you can work with it right from your starting point. Take a clean version with 2 GB.
How many cores in the need?
2. I hope it's enough.
100?
2 gigabytes. That shouldn't be that much. Okay, somehow I broke something. Oh, it's not. Now it's updating. So, please copy that either from your workshop slides to your home directory or from within our common project application, project working directory. If you have this in your home directory, please open it up. So initially, shouldn't that be text? Yeah, that's text, okay. So we're going to explore our LWFA example. First of all, we'll load the Python libraries. Then we're going to use some libraries that are shipped with PIConGPU. So for that, we need to find where our PIConGPU source code is. So I'm just executing some src and PIConGPU. So there's our PIConGPU source code. And then we add this to our Python environment path. Actually, we're adding lib Python PIConGPU. And then we're actually loading one specific backend right here. I think this causes a problem. So please execute this twice. I have to investigate what this is. I had no time to do this beforehand. Second time should work. Otherwise, we're going to just skip that example. Yeah. And then, of course, we have to know where our simulation is, and that's in Scratch, Projects, 5. Okay, I kind of copy paste that.
513.10.
Thank you. Okay, so this pretty much just lets us know for the future where we are. So right now what we're going to use is we're going to use the energy histogram data library, which ships with PIConGPU to extract data. That's fine. This automatically reads in the data available, extracts the iterations. We'll see, okay, these are the iterations we kind of got. These are the associated time steps. Then we extract for a specific iteration, for the last iteration, for 2000, we iterate, we get the, for the species electrons and the filter also all electrons, we extract the number of particles and per bin, and then we just plot that. And we see, okay, nicely, okay, there are a lot of slow particles, but there are few, right now it's still exponential fast particles with higher energies. If you want to explore that, there are more options to do this, like defining a time step of an iteration or providing multiple iterations. So to continue that, we'll just load the OpenPMD data we also created, select a time step that we want to have a look at, see what attributes are there. So these are like common attributes, and Franz covered that there are lots of attributes that you need to set with OpenPMD. This is just an example of what we find. One of these attributes lets us see the grid resolution. So that's what we're going to extract right now. Cell width, cell height. And as Franz mentioned, also OpenPMD stores this in internal units and provides a conversion factor with it. That's our unit length. And in order to get this in meter, which is more common than some weird PIC unit, let's convert that right here. And then we load our mesh. It's the iteration mesh name. This is the scalar mesh. For scalar meshes, you need to add that. I think this is going to change.
Let's change it to scope. We don't need it anymore.
Okay, you can ignore that. Should I try that? Okay, let's hope for the best. Let's see whether this works. That's fine. Oh, amazing. Okay, this hasn't been working before, but with recent updates and with Franz's installation, it works. That makes your life for scalar fields much easier. If you have a vector field, you just add another brackets and, for example, x, y, whatever component you want. We don't want the entire data, so we're going to just extract a slice of it. So this is extracting a slide, getting the unit, flushing the data, so actually loading it, and then doing the conversion. We know what dimensions we have in x and y direction, so use that and our cell resolution to get axis arrays for all values, and then we do plot mesh PLT, where we define our both axis y and x, our density, some color scale, some maximum value, some labels, and then you see, oh, nicely, this is our slice of your electron density through the simulation. You see the laser field imprinted here in the density. There's no laser field visible in that visualization, and then the cavities that are created by pushing the electrons aside, creating that wake in which we can accelerate electrons. There are, of course, many more meshes. And you can all explore this also with the OpenPMD viewer. I'm using the OpenPMD API for Python right here, but you can also explore this with the viewer. For these particles, you see the number of particles. That's going to be the same. We define a handler for a specific species name. Want to know the momentum and the y component. So this is our acceleration direction, load that chunk, get the unit, flush it, and apply the conversion factor. In this case, we have to know that these particles are macroparticles. So simply speaking, they are a collection of multiple electrons. And that means if we're interested in a single electron's momentum, we have to divide this by their weighting, which is like how many electrons do they actually represent. And that's a more meaningful value. So we divide by the weighting. And then for physicists, we try to get rid of units. So we divide by mass of an electron and by speed of light and get a unitless value. Great. Just a number. So let's do that. And then let's plot that. And then we're pretty much done. Oh, no. Okay. That was not enough. So that's exactly what you say if you didn't allocate enough resources. I'll just scroll through it. You just get a nice picture which looks, ooh, that's a bit annoying, looks like this.
So you not
We can put the picture to the.
Great. Yeah.
It's not very complicated to restart the process because you will get, it will show you that state again.
Yeah.
I mean, you need to read some of the job.
Oh, yeah. We can do this now. I mean, we're close to the coffee break anyway. Okay. I will say we have a coffee break right now. You can execute this on your own. I think we are right on time for the coffee break.
Yes, exactly.
Perfect. And then I think I need a few more minutes to walk you through some of the more parameters, and I'll point you to some projects you can explore on your own, and where we can answer your questions if you play around with that. And then Julian will take over and give you some more technical details for PIConGPU. Okay. Then see you in 15 minutes. We will end the coffee break at 15:30 Central European Summer Time. So in 15 minutes. See you then. So klein. Welcome back. So our central computer now stored finally the entire video. I'll wait a second. Okay. You should see, yes, you see. So now I ask for more resources. Hopefully this is now good enough. Yes, it finally made it. And we see a distribution. And since we're not plotting, the energy as before with the energy histogram plugin, but now just the momentum distribution, the main component. We see that exponential decay right here. That is very similar. That's causing energy. But we also have some particles going the other way. These are the ones that are pushed backwards. Again, there are many more particle attributes and values you can study. Feel free to write your own analysis. Yes. Okay, that's all from the analysis point of view. So let's go back to the next part, adjusting simulation parameters. And we'll just quickly go over a few parameters. So the main one is the simulation param file, where we have our grid resolution. We define a base density on which we actually use the plasma density and the typical particles per cell. So if you're familiar with PICO, these are essential parameters. So these can be found in include PIConGPU params, and there we just go to simulation of params. You see, for example, your time resolution, you see your grid resolution right here, as mentioned before, your base density, particles per cell. If you want to adjust these parameters, for example, work at a different density, you have to adjust these parameters. So these are one of the simpler param files. Then let's go to a bit more complex parameter file, and that's the species initialization.param. Species initialization.param defines in a pipeline how you distribute particles in your simulation. So you've got a pipeline called init pipeline, which is a PMAC list, where you define, for example, add particles, change attribute of particles, clone new particles from old particles, and so on. So we can create particles based on a simple density profile. We'll look in the next part how to define density profiles. So create density is just defining a density profile. In this case, we call this Gaussian. Give a start position inside the cell. So we define densities on a cell level, but of course we can distribute particles in a cell, like randomly distribute them, having them on an equal kind of grid, and then what particles we want to distribute there. Of course, we can also say, I did that entire work process once, I don't want to do it again, just copy me, for example, my electrons to my ions, and then just place the ions directly on my electrons, which is a good strategy to initialize charge neutral. And there are many more attributes you can manipulate, like changing the charge state of your ions, or, for example, applying a temperature to your species, to temperature distribution, or in the case of, for example, these astrophysical jets, this KHI instability I discussed beforehand, applying drifts so that you actually get that streaming and shearing surface instability. So we'll just have a brief look at it. So this is species initialization.param. Somehow I can probably activate code highlighting. C++, yes. Does this work? Yeah. So it's probably a bit easier to read. So this is now a bit of a complex init pipeline. So if we don't activate ionization and have no ions, it's pretty much just creating that specific line right here. And then we can, with precompiler flags, define also whether we derive, for example, ions, or whether we don't create that at all and just create electrons, ions, and set their charge state. That's all what we can do. I won't go into detail because Julian also wants to speak quite a bit. Please explore this on your own if you're interested in how to set this up. The next one is, I mentioned already, the density.param. There are various ones that we use. The LWFA example uses a Gaussian distribution. We'll have a look at that in a second. But there are many more profiles you can choose from. And the most easy to use one for anything you want to do is the free formula functor. You define just an operator which gets the position in SI units and the cell size in SI units. Then you write whatever function you want to return, and then you return a value between 0 and some number, let's say 1 being the base density. And then you work with that. You just define that right here, and then you can use that free formula inside your create density. So instead of this. Okay, let's have a look at that quickly. So that's density.param. So this is now just the Gaussian distribution. We have some factors, like it has a negative exponent. It's all described right here in the comment, the power. So it's not a pure Gaussian, it's a super Gaussian with a power of 4. You have some vacuum cells. You have a center left, a center right, where you actually start the Gaussian. In between, it's going to be constant. So it's a super Gaussian with a constant area. You define your sigmas, and that's pretty much it. And then we're using that Gaussian inside our species initialization.param. So right, where was it? Right here. Okay, so that's the density param. And then we already looked at that quickly. That's the incident field.param. The LWFA uses a Gaussian laser profile. That's a bit of a lengthy definition. We'll just have a look at the very end where this incident field is actually defined. So every surface of your simulation volume can introduce these lasers, and in this case we just introduce them from our y minus or minimal surface, and they define that profile there. You see that this is just in using the profile. We'll have a look at that right now. Where is it? Incident field, again just some code highlighting. So we changed that value already to something else. You define the wavelengths, you define the pulse duration, and so on. You see, if you're interested in how to set up lasers, please have that in detail. It's all commented. That defines how values are defined. So, for example, spot sizes, like how large it's transversally, how long it's longitudinally that laser pulse differs on whether you're purely theoretician, then you use sigmas for Gauss, or if you're an experimentalist, then you use full width half maximum of intensity. So all this is clearly described in the comments, and you can set the values you want. What I wanted to show you is the very end, where we actually define this area right here. So this is a precompiler flag where we use this Gaussian profile to be initialized from that. But you can initialize the laser from any plane under any angle. So you can have, as you have seen, have probe pulse coming sideways into your simulation. Okay, I think that's all I wanted to briefly discuss for the setups, and especially for the LWFA setup. There's no time to do that now because we don't run this in parallel. You could, in principle, have a mini simulation campaign by, for example, switching the laser intensity values or the density values and see how this actually changes the wake. So if you're interested in exploring the physics a bit, run the example we did, change your laser intensity or your density and see how your wake structure with that IPython notebook we ran changes. Okay, so for the setup, there would be now time to ask some questions. I don't see questions. None in Zoom, I assume none in Slack. Okay, I'll then quickly go over so Julian has some more time. If you want to go beyond the simple parameter scan that we did, or that you might have done, I will recommend two examples that are easy to play around with on that cluster for the remaining time of that reservation or that workshop compute time. One is the Kelvin-Helmholtz instability. So if you're interested in astrophysics, take the Kelvin-Helmholtz example. There is the initialization pipeline is a bit complex to actually see how you actually create these strings. It's interesting to explore that. Other than that, that's just initializing electrons and protons. Please use a 4.cfg, and you can add, this is not a lot of resources, but that's good for the allocation we have, and add OpenPMD output as in the other examples if you want to see something. If you're more into not electron acceleration, but proton acceleration, please have a look at the foil LCT example. There you can use both 4 and 8 CFGs. They're not very expensive. These are 2D simulation examples to see how proton acceleration actually works. This is something, if you want to look in detail, please explore this on your own. Ask questions via MetaMost or via Slack or probably via Zoom, as long as the Zoom session is open, but Slack is probably better for the next days. Yeah, so just to give you some hints on how to continue. And there's a question.
Yeah. What do the 4 and the 8 stand for?
So the question from the audience, from Julian, was, what does the 4 and the 8 stand for? I didn't go into that. These numbers usually stand for how many accelerators you're using. So 4 CFG uses 4 graphic cards in this case, and 8 CFG uses 8 graphic cards. Again, since this is using TPG, you don't have to care how the nodes are distributed. If 8 GPUs don't fit onto a single node, then it automatically does it MPI distributed 2-node setup, for example. Yeah, you'll see. Be careful. One tends to actually don't rename these values, just change the numbers, and then 4.cfg might actually be a large setup that you just copied. That's a common error. Okay, but that's all. I hope you play around with it, but I will stop now and hand over to Julian. There's a question. These examples are integrated into PIConGPU. These examples are integrated in PIConGPU, and that is. Michael's muted. Michael, do you want to say something? I think he might be in a different conference. Okay. No, he's not trying to. Most likely, doesn't speak to us. They have different groups. Planning. So these examples are part of PIConGPU, so the KHI and so on. And your PIC create should also recognize them automatically. I'm not entirely sure, Maxime, what you mean with that they are different groups. Could you comment? No, they are from our group. But yeah, in principle, if external people are interested in providing a new example, feel free to open a pull request from that. That is perfectly fine. I mean, most of the examples are stuff that we are interested in and that we want to clone from to make our life easier. But of course, we're open to having external other groups also adding examples to our code. Okay, I hope that answers your question. Good.
Can I maybe speak out?
Yeah, of course.
Yeah, my question is related to your laser community, but there is a particle physics community, especially you collaborate with CERN. And maybe you heard about a John 4 package, which is and John 4 package goes with the examples, which is accumulated through the ages of the application and use cases of those package. So that's why my question is targeting that approach. Are you aiming to maybe in the future aggregate those examples and deliver them as a part of your package? But
yes, so we are not actively planning to add as many examples as we can. We are actively working right now on adding small examples for testing. So that's for our testing CI. That's one thing, but we're also adding examples for use cases that are interesting for the community. But these are not a separate repo, they are part of the PIConGPU main source code. If they're becoming larger, one might, so many more examples, one might think to extract them. But I will say yes, I mean, that's the most useful part as a user point of view, to have an example library or lots of examples that you can start from.
Okay, thank you.
Okay. Then I'll hand over to Julian.